Okay, today we are doing alkyl substituents, which is a fancy way of saying that we are working with isomers, which is a new term. It is all about organic molecules, and we specifically are looking at carbon chains that are bonded to other carbon chains. So if you are not an expert at naming alkanes, alkenes, and alkynes, I would go back and work on that first. If you feel moderate, okay, I think actually this could give you some really great practice. So, the first thing that we need to talk about is what an isomer is, which is a molecule that has the same chemical formula but a different structure. So, I think this is best to actually show you in a picture like this one right here. So, this blue molecule, you should very easily be able to identify that this is butane because this baby has 4 carbons and it has all single bonds. Its formula would be C4H10. Now, this green molecule, its formula is also C4H10, but it is not a straight chain. And you may see right here that we have 3 carbons in a row. And in order to wrap in this 4th carbon here, I would need to drag my pen back and go down, which we are not allowed to do. We cannot bring our pen backwards when we are counting molecules. So really what this means is that I have a propane that has a methyl group dangling off of it. So a methyl group is a 1 carbon group, meth, 1 carbon, and that YL tells you that it's dangling off of a different chain. So these guys are isomers of each other because they have the same chemical formula, but they are built differently. The way I like to think about it is the difference between a quesadilla and a burrito. Quesadillas and burritos usually have the same stuff inside of them. It's just the format, right? A burrito is kind of like all wrapped up. You would eat it with your hands, where quesadilla is more like flat. Sometimes it's like chopped into smaller pieces, but really the inside is going to be some form of meat, peppers, onion, salsa, guacamole, whatever. It's all kind of the same stuff that goes inside. It's just the way that it's built is different. So you can think of isomers as burritos and quesadillas. So these guys are going to be named a little bit differently because they are not a straight chain. So that's basically what's happening in this lesson, is the different ways to name stuff when it's not just a straight chain. So these are the rules. I think it's far easier to learn this by practice than by a list of rules, but here's the list if you're a list person. The first thing we need to do is find the main chain. And this chain specifically needs to be all in a straight line, not necessarily a straight line, but you can't count by bringing your pencil backwards and doubling back, and you're not allowed to pick up your pencil and jump around between your different carbons. So you'll kind of see how that works in a hot minute. Then you need to find all of the things that dangle off of this chain. They're technically called functional groups, but I call them dangles. Then what we are going to do is count the number of carbons in that main chain in both directions. We're going to count them forwards and backwards, because just like when we were naming and trying to give the location of the double or a triple bond, we want all of the special things on this carbon chain to give us the smallest number possible, so that it's just easy for all of us to communicate when we're working on the same system. Then our dangles are going to be assigned numbers. We can't mix and match number systems. So all of those numbers need to add up to the tiniest number possible. And then lastly, as we name these dangles, the final name, all of those names need to be in alphabetical order, even if that messes up the numerical order, and maybe we would have 5, 2, bromochloro, etc., etc. For now, we are just working with carbons dangling off of carbon chains. but we will work eventually with other atoms that dangle off of carbon chains. So we are going to start right here with naming this green molecule that I've drawn before. So first thing we do is find our longest chain, which we found is this red line right here. And 3 carbons in a row is going to be a prop. That's the prefix for 3 carbons. And we are still going to give this an ending based on the bond type. So I've kind of drawn through it here, but we can kind of remember that these guys all have single bonds between them. So this would be a propane. And then I have circled our dangle, and this right here is a 1 carbon dangle. You should remember the prefix for 1 carbon is meth, and I'm going to add a YL ending to tell me that this is dangling off of a propane. So I have 1 carbon dangling off of a 3 carbon chain with all single bonds. Now, I need to identify where this methyl group is. So if I were to number my carbons, 1, 2, 3, and then 3, that's not a 3, 3, 2, 1, in both number systems, my methyl group appears to be on carbon 2. So the official name of this molecule would be 2-methylpropane. That tells me I have a 1 carbon dangling from carbon 2 on a 3 carbon single bonded chain. It's a lot of information. It's just the way organic is. There's not really much else to it. So I'm going to draw a few more, and we're just going to get some practice here. So let's say I have, and I'm not going to draw my hydrogens just for the sake of simplicity, because these are going to get real complex real fast. Otherwise, we're just going to assume that these guys have all of their hydrogens attached. This is not the correct way to do it, but let's just say that it is. Okay, so this right here, we have a crazy thing going on. So the very first thing that we need to do is find our longest carbon chain, and there are really 2 paths here. So we can take this path just going straight across, and we would find we have 1, 2, 3, 4, 5, 6, 7 carbons going this way in my green line. And then if I took this red line here, I could start here and do 1, 2, 3, 4, 5, 6, 7. Either way, I'm getting 7. Let's say I started here with this purple line. I'd have 1, 2, 3, 4, 5, 6. 6 is smaller than 7, so I don't want that line at all. I don't think I'm going to find anything bigger than 7. So I am going to just keep this one here for the sake of simplicity. But I need you to identify that this, this piece right here that I'm pointing to with the mouse, this could also be part of my longest carbon chain. Now, time to name this baby. We have 7 carbons, and those carbons are all single bonded. So this would be a heptane. But this is a special heptane because it has extra things on it. So I have 1 carbon dangling over here. A 1 carbon dangle is named a methyl because it's 1 carbon, and the YL tells you it's dangling. And then right here, I have an ethyl. I have 2 carbons dangling. So we could have methyl, ethyl, propyl, butyl, pentyl. The bigger they are, the less likely they are to happen, but they do exist. So that's what I have so far. Now, I know that my name is not just heptane. I have to somehow incorporate the methyl and the ethyl into that name. And what I need to do is specifically identify where those things are. So I am going to number my carbons so that I could give these dangles or functional groups and address. 1, 2, 3, 4, 5, 6, 7. That's my red number system. Now I'm going to number it backwards with green. 1, 2, 3, 4, 5, 6, 7. So my option here is that I could have, let's see, do we have a yellow? We do not. Let's do the gray. We can have 2 and 4 as my numbers that go inside my official name, or I could have 4 and 6. Now, I cannot pick from both number systems. I would need to either pick entirely the red system or entirely the green system. The way I figure out which one to use is that I add the numbers together and figure out which one is smallest. So 2 plus 4 in my red system gives me a total of 6. And in my green system, 4 plus 6 gives me 10. 6 is less than 10, so I'm going to go with the red system. Now, my rule says that my things need to be named alphabetically. So I'm going to look at the name of my dangles. I have a methyl and an ethyl, and according to the alphabet, ethyl should come first. So we're going to have ethyl, methyl. I know this sounds ridiculous. This is actually how it's done. This would be ethyl, methyl, heptane, but I need to give the numbers, and those numbers need to match the order. So this would be 4, 2, ethyl, methyl, heptane. The first number goes with the first dangle. The second number goes with the second dangle. I'm telling you, you just learned this by practice. Organic is a little crazy. So my first number goes with my first dangle, which tells me that the ethyl is on the 4th carbon. Then my second number goes with my second dangle, telling me that the methyl is on carbon 2. And the ending is the base or the main chain. So I have heptane here, and heptane tells me about the main chain. I know all of this sounds ridiculous. That's because organic is ridiculous. These molecules get crazy, but this is the gist of it. This is really as hard as it's going to get for like a high school chemistry level. If you can do this, you can pretty much do anything in terms of isomers. I just want to do one more, and that's it, because I don't want this video to be too long. Let's do this molecule. Imagine it's full of hydrogens, because I don't want to draw too much and make this very cluttered. So the first thing we need to do is find our longest carbon chain, which we can find by drawing a straight line without going backwards or without like looping all over. So the longest group or string of carbons that I can find is 3. You can draw this in literally any way. You can draw it straight across or at any right angle. For the sake of simplicity, I like going straight across. But you could have also done like this, going up, going down, like that. You could have done any of those angles. It's really just going to depend on how your brain likes to see things. I like it straight, simple, left to right. Now, after this chain, we have a 3-carbon chain. It's all single bonds. So you should remember from the previous lesson that this base or the main chain is a propane. And this propane is special because it has 2 things dangling off of it. It has something here and it has something here. Now, each of these is a 1-carbon dangle, so they are 2 methyls. Now, whichever way I number this, both of my methyls are going to show up on carbon 2. Let me prove it. 1, 2, 3, 1, 2, 3. So each of these methyls shows up on carbon 2. So the way that I would name this is 2,2-dimethyl propane. This tells me that I have 2 methyls in my molecule, which I do. I have one right here and one right there. One on the top, one on the bottom. I'm sorry, this program is lagging. I'm moving faster than it. We have 1 methyl on the top and 1 methyl on the bottom, meaning in total I have 2 methyls. That's where that di comes from. Remember, like carbon dioxide, di means 2. I have 2 methyls, and they are both on carbon 2. This is different from having 2 carbons in a string. That's an ethyl. When I have them one on the top, one on the bottom, that would be 2 methyls. Okay? Just to reiterate, I'm going to give myself a new page here. This, with 1 on the top and 1 on the bottom, is a dimethyl. And dimethyl is not the same as an ethyl, where maybe I would have something like this. And let's erase this rogue line here. Come on. I don't know why it's not erasing. There we go. That would be different from having 2 carbons like that. This here would be an ethyl because these 2 carbons make like a baby chain, right? This is a baby chain, and then this is one baby chain, and that's the second baby chain. So it's important to see the difference there. These things are different from each other. This is as hard as it gets. It's just something that you learn by practice. I'm going to call it here because I don't want the video to get too long. Definitely rewatch. If you have questions, leave them as a comment and I will do my best to get back to you. And that is all. Bye.